Now come to the next point. Inductors in the circuit. So under this we will discuss कि whenever inductors are connected in a circuit, then how we have to use those inductor and how those can treat. See, this is the inductor having self-inductance L and I is the current. So first of all, when I is the current and if it is given di by dt is equal to 0, or we can say I is here constant. It means current through this inductor is not changes. So there is a flux and that self flux is given as L into I. The flux will be there, but since current is here constant, so EMF will not be there. So there is no induced EMF if I is here constant. Then the same inductor does not produces any EMF. So it just like current carrying simple conductor like this. So no need to do anything. Here induced EMF is 0. So you can replace, it is just like a wire. It does not mean it is normal wire, but it will not produce any the EMF induced. It has stored some energy. Similarly, so this is the first case when current is 0. Similarly, if current is your not constant, let I is the current here, L is the self-inductance, and di by dt is greater than 0. Greater than 0 means here current is increasing. Current is increasing. So when current is increasing here, so here flux, self flux through this coil will also increase, and that self flux since increases, so EMF will develop. So according to Lenz's law, induced EMF will be such that it opposes the change in flux. So here we can have a EMF develop, and this end will be at higher potential, this end will be a lower potential, and E value written as L di by dt. So in that case we can say it is this type of case, means whenever in the circuit it comes, then we can make it is just like a source of EMF, and the E value is given as L di by dt, where I is increasing or di by dt greater than 0. Similarly, in the third case, when let current is decreasing, I is there here, but di by dt is here less than 0, or current is decreasing. Current is decreasing, so EMF will be there, but that EMF must have to maintain the same flux. Since current is your decreasing, the flux of this your decreases, so polarity, EMF polarity will be like that. It is trying to increase the flux. So it is written as E is equal to your L di by dt, or it can be replaced with a cell of this type of polarity in this manner. The E is your L modulus di by dt, where I is decreasing, or we can say di by dt is less than 0. So whenever in the circuit we have kept our inductor or solenoid, so you can treat like this, in that manner. Now here itself we can calculate the energy stored and what is the meaning of this. See how this situation arises. First, if I am talking about this, let in this case current you are increasing. So if this is the case here, it is just like the case of charging of a cell. So when cell charge, so current, it means current is flowing in that direction. That indicate the terminal potential of the cell is more than the EMF of the cell. So the current is going into the cell. So this is the case of charging of the cell. Or this inductor is gaining some energy, and that energy is nothing, it is the magnetic form of energy. Similarly, if we are talking about current in through the higher potential terminal, so that indicate here the terminal voltage of the cell is less than the EMF of the cell. That's why current is flowing in this direction. So that is the case we can treat it is just like a discharging of a cell, or whatever energy this inductor have stored earlier, that energy you are decreasing or dissipating through any resistance. And this is the case here, it is already charged. When the inductor is totally charged, means inductor have gained full of energy, then there's current in the circuit become your constant. So that case also can be said as a charging, means energy stored by inductor, charging, or energy is stored by inductor. And here we can say discharging, or energy loses by inductor. So now we will calculate how much energy is stored by inductor. Now next is the energy is stored by an inductor. Energy is stored by an inductor. So this is our inductor having self inductance L, I is the current, and di by dt is greater than 0. So when di by dt greater than 0, so here since flux is your increasing, so EMF develop here, that is equal to L di by dt. So it is just like this type of case where it acts just like a battery or charging, and EMF of the cell is your, so power dissipated or energy, we can write here power dissipated across inductor P is equal to your E into I. So that power can be written as E L di by dt. This is the instantaneous power, di by dt into I. Then integrate. The P is equal to your L I di and P dt. So P dt is the energy, U half Li square. So energy is stored in an inductor is given as, so energy is stored in inductor is given as U is equal to half Li square, where L is the self-inductance of inductor. Self-inductance of inductor, as L is equal to mu naught N square V, then energy U is written as half mu naught N square I square into V, or this further we can write mu naught Ni square by mu naught into V, and this term is nothing, it is the magnetic field inside the inductor. So U is equal to half B square by mu naught into V. This is another formula. Or energy density then. Energy density small u is your energy per unit volume. Energy per unit volume. So this U is your capital U by V, and which is written as half B square by mu naught. B is the magnetic field on the given volume. So where B is a magnetic field on given volume. Like this. So energy stored by an inductor, general formula we can write U is equal to half Li square, and much more general in terms of energy density U, energy per unit volume, U is your capital U by V is the volume, which came here 1 by 2 B square by mu naught. Now come to the next point. Now see the combination of inductors. Combination of inductors. So first let series combination. It means if a number of inductors are given in series, then how we can replace with a single inductor like this. Let we are having 3 inductors of self-inductance L1, L2, L3 between A and B, and we want to replace this with a 1 between B and A. That is written as L equivalent. So just I am connecting here with a source. If I is the current here and di by dt is your greater than 0, so this will be also in the same way. I is the current and di by dt is greater than 0. Now let we are having potential V here, also potential V. As the current you are increasing, so here also EMF develop. Let L1 into di by dt. Similarly, across L2 EMF develop. Across L2 also in the same way, E2 L2 into di by dt, and across L3 also E3 L3 into di by dt. In the same way, if we are looking here, this is your positive and negative, Here L equivalent into di by dt. Let this here E. So these are the different values of EMF induced in the different inductors. Now we can apply here Kirchhoff's law like this. We can apply here Kirchhoff's law. When we are applying, so from Kirchhoff's law, see here, minus E1 minus E2 minus E3 plus V, this is 0, or E1 plus E2 plus V. Substitute the value of E1, L1 di by dt plus L2 di by dt plus L3 di by dt is equal to your 1 is equal to V. Let this is the equation number 1. So that can be further done as L1 plus L2 plus L3 into di by dt is equal to your V. Similarly, if we are applying Kirchhoff's law here, see, if we are applying Kirchhoff's law here, so we will get minus E plus V, this is 0, E is equal to V, and E further written as L equivalent di by dt is equal to V. This is let second equation. So now from equation 1 and 2, from equation 1 and 2 we can write here L equivalent is equal to your L1 plus L2 plus L3. This is the value of L equivalent. So when the inductors are connected in series, so effective value of self-inductance written as L1 plus L2 plus L3. Now see the second one here. Parallel combination. Suppose we are having number of inductors which are arranged like this. This is one of the inductor. This is another one. And let this is your third one. These have some value L1, L2 and L3. Let these are the point A and B. We want to replace all these three with a single one like this, A and B, and the value of this we can say L equivalent. Now if I am connecting from a source of EMF V, so due to that let I is the current here, that current I here distribute, let here your I1, here I2, here I3. Similarly, if we are connecting this with also one of the source and here current your I, the first thing here, as just we are connecting as di1 by dt greater than 0, di2 by dt also greater than 0, and di3 by dt also greater than 0 as current here increases. So here we can assume di by dt greater than 0. Then what will be the factor here? Due to increasing current here, EMF develop. How much EMF here? L1 di1 by dt. Here EMF L2 di2 by dt. Here EMF L3 di3 by dt. In the same way, as current increases here EMF is your L equivalent into di by dt. Likewise, from here we can write first law of Kirchhoff. From first law of Kirchhoff, I is equal to here I1 plus I2 plus I3, or we can write di by dt is equal to di1 by dt plus di2 by dt plus di3 by dt. Let this is the first equation. This is from Kirchhoff first law. Now we can apply Kirchhoff law in the second law in the all loops. If I am applying Kirchhoff second law in the let outer loop, similarly we can apply Kirchhoff second law in the middle loop, then in the lower loop. So if we are applying first in the lower loop, minus, you can write from second law of Kirchhoff. From second law of Kirchhoff, minus L1 di1 by dt plus V, this is 0. So di1 by dt is equal to V by L1. Similarly di2 by dt V by L2 and di3 by dt V by L3. Let this is the equation number 2. And now from here, from this equation, here we can apply Kirchhoff law. So minus L equivalent di by dt plus V, that is 0. So di by dt is equal to your V by L equivalent. This is your third equation. Now substitute the value of second and third in the first equation. We can write from equation 1, 2 and 3. If I am writing here di by dt or V by L equivalent is equal to di1 by dt, that is your V by L1, then V by L2, then V by L3. So 1 by L equivalent is 1 by L1 plus 1 by L2 plus 1 by L3. This is the relation for L equivalent. 1 by L equivalent here 1 by L1 plus 1 by L2 plus 1 by L3. So this is called your parallel combination of inductors. Now come to the next point. Let's see one of the example based on self-induction. See, let this be a part of circuit. A and B, and R value let your 5 ohm. Self-inductance given let 2 Henry, and this is your 10 volt, and this is your 2 ohm. So if I is the current here, so we can write here AB is a part of circuit at any instant, current in the circuit is I is your 2 ampere and di by dt is let 0.2 ampere per second. So question is that find potential difference between point A and B. This is the question here. So first of all, see how to solve this one. In this here, di by dt is given here 0.2. It means current changes with the time. Current here increasing with the time. So when current increasing with the time, so this act as a positive terminal of induced EMF, and this will be negative because current direction is this. So that current here increasing the flux here. So induced EMF will be such that it decreases the flux. So induced EMF value written as L di by dt. Now from Kirchhoff's law, we can solve. Let us start from A to B. VA, then minus 5I minus L di by dt minus 10 minus 2I equal to B. So we can write here VA minus VB is your 5I and 2I, 7I plus L di by dt plus 10. 7I. I is given here 2 ampere, 7 into 2, 14 plus L given here 2 Henry, di by dt here 0.2. So this will be a 0.4 plus 10. Finally answer is your 24.4 volt. This is the potential difference between A and B. Likewise, we can solve. So now come to the another example. Now this is the one of the circuit given here. So here one capacitor of capacitance 2 farad and 2 resistance R1 2 ohm, R2 3 ohm, and one inductor of self-inductance 4 Henry is given. In the different branches, current has been shown. In this branch, current is your I1, in this branch I2, and the current in the inductor branch is given your IL. And here it is given potential difference between the inductor can be said as here VL, this is higher potential. Now, and potential difference across the capacitor is given VC, and this plate at higher potential, this is lower potential. See, at any time t, at an instant, I1 value your 10 e to the power minus 2t given. It means current I1 vary according to this relation. I2 value here your constant, this current your constant, which is given your 4 ampere, and potential across capacitors VC, that is given as 3 e to the power minus 2t ampere. VC is equal to 3 e to the power minus 2t ampere, like this. These are the different values are given. Now we have to calculate the value of IL and the current across inductor, potential across inductor, potential difference between A and C, potential difference between A and B, as well as potential difference between C and D. So first of all, how to calculate all these values. See, if I am looking the charge on capacitor, see, charge on capacitor. Capacitor at this moment Q is equal to your C into Vc. Capacitance given 2 farad, Vc given here 3, it become your 6 e to power minus 2t. Now, so what we can say here, if I am looking the current in that branch, IC dq by dt, which is nothing here, minus 12 e to the power minus 2t. The current value comes here negative. Current value comes here negative. That indicate here charge on capacitor your decreasing, as well as from the charge versus time graph, Q versus T graph, if I am plotting, T0 charge here 6, T infinity charge will be 0. So that type of charge versus time graph is coming. So that is the charge versus time graph. From here it indicates charge on capacitor you are decreasing. It means positive charge on capacitor is going in this direction. So charge decreasing, positive charge going in that direction. Direction of flow of positive charge means IC value will be in that side, and minus sign only that indicate the charge is your decreasing. And once you have defined the direction, no need to take the final negative sign here. So IC is equal to written as 12 e to the power minus 2t. This is the current in the capacitor circuit. Now, once we have found the value of current here, so at junction, let O, if we are using Kirchhoff first law, so from Kirchhoff's first law, at point O, incoming current is equal to your incoming current is equal to outgoing current. So at junction O, incoming current your I1 and I2, outgoing current your IL and IC. So I1 plus I2 is equal to your IC plus IL. And I1 plus I2 we can get from here 10 e to power minus 2t plus I2 your 4. IC already we have found right now 12 e to power minus 2t plus IL. So IL will be here 4 minus 2 e to the power minus 2t. This is the variation of current in this circuit. Now, if I am plotting a graph between IL versus time, so T0 current will be your 2 ampere, T infinity current is your 4. So this type of graph we will have like this. This is the 2 and this will be your 4. So we can say current here you are increasing. The current is increasing. So polarity is your exactly correct polarity we have found here. So now, so VL, the first IL value we got here, IL value is this. This is the IL. Now VL is your L DIL by dt, and L value already we have found here 4, it is given 4, and DL by dt we can get from here 4 into DIL by dt. DIL by dt, if we are differentiating this one, this becomes here 0, this is here 4 e to the power minus 2t, this will be your 16 e to the power minus 2t. This is the VL value. After getting the IL and VL, now we can apply Kirchhoff law between A and C. Now for A and C point, apply here VA minus 2I1 plus 3I2 is equal to VC. VAC is your 2I1 minus 3I2. Substitute the value of I1. I1 value given here 10 e to the power minus 2t. So 2I1 20 e to the power minus 2t minus 3I2. I2 your 4 into 3 12. This is your VAC. Similarly, if we are looking VAB, apply Kirchhoff law from A to B. See, for A and B point, VA minus 2I1 plus VC, which is your VB. So VA minus VB, 2I1 minus VC, and 2I1 is your 20 e to the power minus 2t, and minus VC value given 3 e to the power minus 2t. So VAB is equal to your 17 e to the power minus 2t. Likewise, we can get the between C and D also. We can apply Kirchhoff law between C and D. So this is the one another example, and with the help of this we can get idea how we have to use inductor when it is in the part of circuit.